Okay, so for the next one, H2O2, hydrogen peroxide, actually is interesting because it has two oxygens connected to each other and then the hydrogens kind of hanging off of it. So it looks kind of like a pair of glasses. And each one of these oxygens has two sets of unpaired electrons. So I'm going to pick a central atom to figure out the geometry, and it's going to be one of the oxygens. It doesn't matter which one you choose. But so we're going to look at this oxygen, for example. This has two bonding and two non-bonding domains, which means it has a bent shape. And bent shapes are always polar because you can draw a dipole. And so again, it's going to go from the positive side, which is kind of going to be the bottom down here, towards the electrons, towards the negative side. So there's our dipole. Okay, so if I can draw a dipole, then that means that this is not a symmetric molecule, right? There's negative charge on the top of it and no positive on it to balance it, basically, on the top. So that means this is a polar molecule. Okay, once I've decided something is polar, I need to determine if it is going to have dipole-dipole, hydrogen bonding, or ion-dipole interactions. There's no ion here, it's just hydrogen and oxygen, so there's no metal. So it's not going to be that. It does have a dipole, so it could be that. However, I know that if oxygen and hydrogen are attached to each other, like this, that's capable of hydrogen bonding, which is a pretty strong intermolecular force. So what this tells me is if I were trying to rank all of our materials so far, we said that this one would be the weakest, this would be the next strongest, and this would be very strong. So hydrogen bonds would be the strongest. So from 1 to 3 is like weak to strong. That means that as we get closer to the 3, to the H2O2, it's more likely to become like a solid. Okay. All right, so the next one is ammonia, Nh3. All right, so we're going to start with nitrogen in the middle. And nitrogen has 5 valence electrons, so I'm going to put in my 5 like that. And then each hydrogen has 2, so I'm going to, each hydrogen wants 2. It has 1 to begin with, so we're going to make bonds like that. And so this is the Lewis structure for NH3. This has 3 bonding domains, that's between the N and the H, 1 non-bonding. So when you have this, it leads to the shape trigonal pyramidal. And trigonal pyramidal is never symmetric either because you have this negative charge on the top. And so that means that the electrons are going to kind of point towards, the dipole rather, are going to point toward the electrons. So this is a polar compound as well, which means that I have to decide what kind of forces it has. Let's see. It could be dipole-dipole. It's not ion-dipole. I don't have a metal. But I also remember that hydrogen bonds are defined as anything when you have an NH, an OH, or an FH, right? So if that's true, this is NH. So this is also, this is also a hydrogen bond. Now, if I wanted to rank these, I got to figure out whether H2O2 would be a stronger hydrogen bond or NH3. The answer to that is pretty complicated, but it kind of boils down to the electronegativity difference between OH and NH. Now, I don't actually need to calculate this because I can just kind of remember that the trend on the periodic table, so if this is your periodic table, the trend is that electronegativity increases as you kind of go toward the upper right corner. So then I look at oxygen and nitrogen, and they're next to each other, but oxygen is farther to the right. So that means that the OH interaction is probably going to be stronger because oxygen is more electronegative. So it's pulling the electrons away from hydrogen much stronger than the NH bond does. Okay, so that means not only is this a hydrogen bond, but it's a stronger hydrogen bond than the one we had from hydrogen peroxide. So we could rank it as number 4. Okay. Calcium chloride. This one's tricky because it's an ionic compound, right? All the other ones above that are covalent. So this one, if it said AQ, then we would be envisioning the calcium ions being surrounded by a bunch of waters. And when that happens, the oxygens kind of point at the water, right? So if we're going to draw the structure, it would look like this. And so this would be an ion-dipole interaction. However, the question doesn't actually say that it's aqueous, so that's a little bit misleading. If it doesn't say that it's aqueous, then we have to assume that they're really talking about the ionic bonds here. That's what's holding this thing together. And we know that ionic bonds are super strong. So that would be the strongest one in the list. It's also likely to be the strongest one in the list in aqueous solution because we know from our prior diagram over here that ion dipole interactions tend to be pretty strong, and in particular they're strong when you have really high charges, like a 2+ is pretty high. So either way, actually, we end up with the conclusion that calcium chloride is probably the strongest intermolecular force. So again, it's ion dipole if it's dissolved in water. All right, so what I want you to do on this last part is to essentially do the same thing I just did on the last slide. I want you to tell me whether the following substances, basically to rank them by strongest IMF. All right, so let's list a bunch. Okay, so what I want you to do here is the same process. You need to draw a Lewis structure. You need to explain the shape. Use that to get polarity of the molecule. And then from there, tell me what the dominant intermolecular force is. After you've done that for all of them, rank them from the weakest up to the strongest.